Hello everyone, welcome to another video. And in this video, I'll be going over permutation sequence, a hard problem. In this video, I'll be going over the problem, then explaining the solution and the intuition behind it, and then I will explain how to actually implement the solution, and then at the end, we'll just wrap up, talk about the runtime and analyze the solution. So let's get right into explaining what the problem is asking. So in this problem, don't worry about this. This is the implementation that I'll be explaining later. So in this problem, you're given two integers, n and k, and you're supposed to return the kth permutation sequence. So the permutation sequence is just the order of these permutations, right? So with n equals 3, you can permute it like this. So like 1, 2, 3, 1, 3, 2, and they're just ordered by like least to greatest in terms of how they're permuted. So yeah, it's pretty straightforward. 1, 2, 3, and then 1, 3, 2. So you get both numbers that are in the 100s first, then you get the two numbers that are in the 200s with these two other digits permuted, and so on. And this would be the permutation sequence for n equals 3. So you're supposed to return the kth number in this sequence. So when k equals 3, you should return 213. And they just have a couple other test cases here. And the constraints for this problem is that n is between 1 and 9. And obviously k is a valid permutation sequence because there are only n factorial permutation sequences as seen here. So now that we know what the problem is asking, let's go over the solution. So at first thought, you might be actually able to, you might be thinking that you can just directly brute force the entire sequence, like just generate the entire sequence, then just pull the number at the correct index. But this brute force strategy actually doesn't work. I tested it just to make sure, and it does give a time limit exceeded error. So we need to be a little more smart about how we generate this sequence, and we can do that by making the following observation. So when we look at this sequence, we know that for n equals 3, there will be some numbers that start with 1, there will be some numbers that start with 2, and there will be some numbers that start with 3. So ideally, we can figure out which number we need to start with. Instead of having to generate all of these, we can just say, let's start with 2, and then reduce that to a problem with only 2 numbers. So what I mean by this is, in this example, n equals 3 and k equals 3, we know that there are 2 numbers that start with 1, and there are 2 numbers that start with 2, and there are 2 numbers that start with 3, just looking at this. So we know that because k equals 3, the correct number should start with 2, because we know the first 2 elements would start with 1, so obviously the third element would start with the next number. And we can calculate the size of these groups, like the group that starts with 1 has a size of 2, all these groups have the size of 2. We can calculate the size of these groups by doing n minus 1 factorial. Because if you think about it, if we have 3 numbers here to choose from, and we fix 1, then we're left with all the ways to permute the rest of the sequence. So after you fix 1 number, you'll have two numbers left to permute, and 2 factorial would equal 2. So when you fix 1 as the first number, you know that there will be 2 sequences that begin with 1. And for example, if n is equal to 4, then we know there will be like this group of 1s, but we'll have 3 numbers here. So then there will our group would be 3 factorial size. So we'd have 6 numbers that start with 1. So something like 1, 2, 3, 4, and then you can fill out the rest, right? 3, 2, 4, and we'd have 6 of these numbers because we'd have 3 other numbers to permute once we fix that first number. So now the idea behind the solution is, since we don't need to generate all of these, we can just skip until we get to the group that is the right group. So for example, if n equals 4, let's just use their test case. So n equals 3 and k equals 3. So we know that each group, there will be some numbers that start with 1, there will be some numbers that start with 2, and there will be some numbers that start with 3 up till n, but n is equal to 3. So now we know, we can also know that because there are 3 numbers, once we fix one, there will be 2 factorial ways to arrange them. So there will be 2 numbers that start with 1, because 2 factorial is 2, and 2 numbers that start with 2, and 2 numbers that start with 3. So now, instead of permuting this entire group, we can just skip groups until we find the group with the right starter. So we know we want to be looking for the third element. There are 2 elements here, so we skip these 2. We know there are 2 elements here, so we know that our correct number is somewhere in the group that begins with 2. So now what we can do is we can, let's say we have an answer here that with n characters, we can just put 2 as the first character in our answer. We can just put 2 as the first number in our answer and move on to permute the rest. So now, because we knew we had choices of numbers 1, 2, and 3, we can get rid of 2, and now we have to permute 1 and 3. So we can do the same thing. So now n equals 2, because we have 2 numbers to permute. So n equals 2, and we need to find the second sequence of 1 and 3. We need to find the first sequence of 1 and 3, because we know k equals 3, so we skipped one group here of 2, so now we can subtract 2 from k, because we're looking for the third number, because k equals 3, and we know we skipped the first and second number because they began with 1, and now we're in this group with numbers beginning with 2, so we can just subtract all the numbers we skipped from k, because we've already skipped that many numbers. So we skipped the first and the second number, so now k will equal 1, and we fix this number as 2 because we know it starts with 2, and we have 1 and 3 left to permute. So now we know we want the first number inside of this group that starts with 2, because we skipped 2 numbers, so k now equals 1. You can subtract the numbers you skipped from k. And now we'll have one less number because we fixed 2 as the first number, so n will equal 2. So we can do the same logic to fill out the second number. So we know k is equal to 1, so we want the first number inside of this group. So we know that there will be some numbers that start with 1 here, and there will be some numbers that start with 3. And using the same logic, we'll know that this group that starts with 1 number, well, after you fill out this number, the last number is just fixed, so this will be a group of only 1 number, and so on. But so this isn't that relevant for a small number like n equals 3, but the logic will work if there are more than, if n is greater than 3 as well. So then what you can do is, you know you're looking for the first number, so you know that it's in this first group, because this group has 1 number and you're looking for the first number. Let's just say you were looking for the second number, k is equal to 2, so instead of initial k being 3, let's say k, this would be the initial value of k equals 4. So you'd still figure out that because k equals 4, we know that the third and fourth number are in this group that begins with 2. We'll still get into this case, but now because we know we want to find the second number inside of this larger group that begins with 2, we know that this group has one number and this group has one number as well. So because we know that starting with 1, like fixing 1 in the second position here, has a group of one number, we can just skip that because we know we're looking for the second number in this larger group here. So then we know that our answer must be in the group that starts with 3, because this group will hold the second number. And then we can fill out 3 here, and well, the last one, we only have one number, we can just fill that out with 1. So when k is equal to 4, we'll return 231. When k is equal to 3, we'll return 213. And this sort of logic will work for greater values of n as well. So yeah, so that's essentially how you work out the solution. You sort of recursively just skip all these groups that you know you need to skip, and then once you stumble upon the right group, you fix that number and then move on and then try to find the next number, and you subtract how many numbers you skipped from k. So yeah, so let's look at how that's implemented. So the way I do it is, first I just, because you want to return a string, I just have a character array here, and we know the answer is going to be of length n because that's how long the permutation is. So yeah, so we first initialize that, which is going to be our answer. Then we have a list of characters, and these are all the characters that we can choose from. And so what we're doing here essentially is by casting this to a character, by adding the ASCII value of 0 to it, we're essentially having characters in our list that look like this. So if n equals 3, our list will look like 1, 2, and 3. And these are just the values that we can pick from. Like these are the values that we need to still permute. So then we get to the actual logic here. So now here's where we fill in the numbers one by one. So what this for loop is essentially doing is it's finding the first number in our answer, then fixing that, then finding the next number in our answer, then fixing that number, then finding the next one. So this I represents which number we're trying to find currently. So we just have a helper method here called getNext, and this will return the index of the next group. So in our function here, this is just a factorial function. It just returns the factorial of a number. So RP will represent the size of the groups. So factorial n minus 1. So if we know there are 3 numbers and we're trying to fix the first one, when we fix the first one, there are still 2 numbers to permute. So RP would be 2 factorial here, and that would mean that we would have groups of 2. So now we go through all the groups. So because we know there are, we know we have n numbers, so like 1, 2, ... to n, we know that there are n groups, and we know how big each group is. So then we can just go through these groups, right? So this is how many elements are in the first group. So the first group will contain the first 2 elements. And so if k is within that group, then we do this thing, which I'll explain later. But when we go to the second group, then we know we're looking at the first 4 elements. So we can check if k is between that. So then we'll find essentially the group with the correct starting number. And And then once we know that, we know we need the ith group, so the first, second, or third group. So then I just return a array here with the first number here that represents the group that we want, and the second number here is just subtracting how many numbers we skipped from k. So this is the size of a group, and this is how many groups we skipped, because if we find the second group, we skipped one group. So we know we are already past the first two numbers, so we can subtract that from k, because we'll essentially, what we want to do is want to find, instead of finding, oh, we want the fourth number in this large group, we'll first fix this number and then be like, we either want the first number in this small group or the second number in this small group that starts with 2. So that's how I want to subtract the number we skipped from k, because we're essentially only working with this small group now. And so this is how many groups we skipped, and this is the size of each group. So because, let's just say in our example here, we know we want to be looking at the second group, we'll subtract 2 from k, because the second group minus 1, and then that's just, we know we skipped these two numbers. So we'll just use that function on our current size here, which is n minus I, because we start with n choices, then we'll have n minus I choices, right? So I'll just set k equal to this thing, which is what we calculated k needs to be, and then we will set that index in our answer to the correct choice in our list. So this is the index of the group, because since we have since this list is 0 indexed, and this is essentially 1 indexed because this will start at 1, we know we want to subtract 1 to find the right group, and we will just remove that from our list. So for example, if our list contains 1, 2, and 3, and we figure out that we want a number that begins with the number in the second group, we will fill that out in our answer here by writing 2 first, and then we'll remove that, because we remove that and we write it here in our index. And then our list will have 1 and 3 as options, and we know k will be equal to 1 because we'll want the first number in this smaller group. So now we can just permute 1 and 3, right? So we know there are some numbers that start with 1, some numbers that start with 3, but we know because this group is size 1, we'll know we want the numbers that start with 1. So then we'll return the index of that, and that's 1. But let's say we wanted, let's say we had k equals 4, and we wanted the group that starts with 3, we'll return 2 because we want the second group. So we can just look, because this is removed, this is now the index of the second group. So then we'll fill it out with 3. So that's how it'll work for either one. So we will remove the group that we want. So this is the index of the group that we want, and we will just set that character equal here. And after filling in all of these like spaces here, then we know we have the answer, because we essentially selectively chose these groups until we filled out all of them. So this way it's a lot better, because instead of generating every single permutation, you can first skip a large chunk of permutations, and then you have a smaller group of permutations, and then skip whatever you need to do in those, and then even smaller group of permutations. So you're essentially removing a ton of the permutations you would have otherwise needed to generate. And yeah, so let's just submit this to prove that it works. And yeah, so it's really fast. It's faster than 96.7% of submissions. And this was the original submission where I thought you could use brute force here, because yeah, but fails on the later test cases. And yeah, so that's about it for this video. I hope you enjoyed, and thank you very much for watching.